So our last section in Unit 3 is on linear approximations. The basic idea here is we are going to use the equation of a tangent line to approximate a y value of a function. Okay, so it kind of says that here, use the equation of the tangent line to approximate a y value for a certain function. So we all know the equation of the tangent line is y minus the y value f of a equals f prime of a times x minus a. Now, if you just take this equation of the tangent line and we solve for y, we would get this. And that is our linear approximation. Okay, so linear approximation, the only difference here is now instead of y equals, it's L of x equals. And this is all this is this is the y value of the tangent line. It's just this equation of the tangent line solved for y. Okay? So to find the linearization of the function f of x equals root x plus 3 at a equals 1. So just so we have an idea of what's happening, I will draw a graph. You do not have to draw a graph for these, but I will draw a quick sketch. Square root of x plus 3. You have to know what it looks like to graph it. And we want linearization at a equals 1, which would be that point right there. Okay, so to do this, linearization is L of x equals f of a plus f prime of a times x minus a. Okay, and what's a? A is 1. So right away, I know my linearization is going to be f of 1 plus f prime of 1 times x minus 1. I'm sorry, x minus 1. Now, I hope you're saying, but that's just the equation of the tangent line, and that is all that we are doing. Okay, what you're doing, if you draw a tangent line at 1, we're saying if we're really close to 1, the y value of the tangent line and the y value of the curve are very close to each other. So we're going to use the actual tangent line to estimate the y value of the curve. Now, the further what you get from 1, the further away the estimates aren't as close. Okay, so now to do this, you just have to find f prime of 1. So go ahead and find the derivative of this. Should be able to do pretty quickly. 1/2 x plus 3 to the negative 1/2, which is the same as 1 over 2 root x plus 3. Plug 1 in, and we get 1/4. So come back over here, f of 1, if I plug 1 into the actual function, I have 2. So I have 2 plus 1/4 times x minus 1. There's my linearization of that function. What is that? That's the equation of the tangent line at 1. Okay, now if I plug in a different x value, I can just approximate the y value of that. So if I plug 2 in, if I plug 2 into this, all that's doing is giving me the y value of the tangent line at 2 instead of giving me the actual y value of the curve at 2. Okay, and if you look down below, I have this chart. So from that equation that you just found, from the linearization, which is 2 plus 1/4 times x minus 1, which I can simplify it to 7/4 plus x over 4, if you just simplify it. So when x is 0.9, the actual value of the function is 1.9748476. If you plug 0.9 into this, the tangent approximation, you get 1.975. Okay, they're really close together. If you do 0.98, you get 1.995 here, and you get 1.99499 here. You could continue. Okay, if I plug 1 in, now the linearization gives me 2, and this gives me 2. Now, why are they the same there? Because that's where you were finding the equation of the tangent line. That's where you were finding the linearization. So that's going to be the same. Yeah, I can continue doing this. Your book shows it. If you go all the way to 3, it's 2.5 and 2.449. So again, the further you'll get away from 1, the further these are going to be apart. That's all the idea is there. The closer you are to 1, the closer the linearization, which is the tangent line, and the actual value of the function. Okay. Now we could use this linearization to approximate the square root of 3.98. So now the linearization right here, I can use that to approximate 3.98. Now I don't plug 3.98 in because you have to think the original function was x plus 3. So for 3.98, x would actually be 0.98. So I'd be plugging 0.98 into the linearization. 0.98 over 4, and I get 1.995. Okay? And then I could do the same thing for the square root of 4.05. What's the actual x value based on the function? It would be 1.05. So I'd be plugging 1.05 into your linearization. And I get 2.0125. Now, are these overestimates or underestimates? So all you have to think about is these are your actual y value. I'll draw it again. I'll get it in right here. 1, 2, 3. There it is. Okay? So when x is 0.98, here's 1, right? 0.98 would be here, a little bit to the left. So this is the y value of the tangent line at 0.98 versus the actual function. So would that be an overestimate or an underestimate? Well, it would be over because the tangent line is over the curve at that. If you look, the tangent line is over the curve. If the curve went the other way and the tangent line was under it, then it would be an underestimate. Okay. So I have another application problem and then just 2 more linear approximations. So for what values of x is what we just got, here's our linear approximation, accurate within 0.5. Okay, so that's basically saying how close do you have to be to 1 where the difference of the actual function and the y value of the tangent line are within 0.5. So algebraically, how are you going to set that up? We're going to say within 0.5, the difference of the function, which is the square root of x plus 3, minus the approximation. We want the difference of those two to be less than 0.5. And the difference, we're going to do absolute value because I don't care if it's bigger or smaller as long as it's within 0.5. Now you would just go ahead and solve this. You could use your calculator to solve this. You could set up 2 inequalities here. You know what you remember absolute value is less than 0.5 and what greater than, this is more the idea of what you're doing here, greater than, 7/4, greater than negative 0.5. And then you could actually solve these on your calculator. You should get this to be within negative 2.6 and 8.6. So as long as I am between negative 2.6 and 8.6, the y value of the function and the y value of the tangent line will be within a half of each other. And then I could do the same thing within 0.1. So it would look the exact same thing. It would be the absolute value. All that means, guys, is that these two, the difference of the function and the approximation, now I want to be less than 0.1. And just to give you the answers, you get negative 1.1 is less than x, which is less than 3.9. So now if I want them to be within 0.1 of each other, I'm even closer if you look. I can go from negative 1.1 to 3.9. Okay. All right, so then I just have 2 more problems. You could pause this and try 3 and 4 right now on your own if you think you understand. It's just straightforward. Find the linear approximation. So here's the function, and I want to do it near what? Pi over 4. So here's my a value. So I can just do what? Linearization equals f of a, which is f of pi over 4, plus f prime of a times x minus a. Now you just have to find all the values. Okay, so f of pi over 4 is 1. Tangent of pi over 4 is 1. Plus f prime of pi over 4. So what? Come to the side. F prime would be secant squared of x. And then you'd have to do secant squared of pi over 4. And you get 2 times x minus pi over 4. There's my linearization. It's not asking me to use it, but all that is saying is the y value of the tangent line is equal to this when I'm near pi over 4. Okay, and then the last one, again, go ahead and pause it. Try to do it. So I have linearization is going to equal f of a, f of negative 1. Sorry, this should be negative 1. Change that to negative 1. I did it as negative 1. Okay, f of negative 1 plus f prime of negative 1 times x plus 1. Go ahead, do f of negative 1. So plug negative 1 into the function. You should get negative 6. Go ahead, find the derivative of the function and plug negative 1 in. You should get 2 times x plus 1. Okay? And then you can use this, and then I could take it a step further. I could say use the linearization to approximate when x is 2 or x is 0. And I could plug 0 in there. And again, the important thing is linearization is using the tangent line, the equation of the tangent line, to approximate the y value of the actual function. And it's only going to be close if I'm near the value. So think about, I'll go back just for a second. Think about the first problem I did, square root problem, 1, 2, 3. Okay, and I have a tangent line. As I get further and further away from 1, if I'm over here, these two y values would not be very close to each other. But the closer I am to 1, the y values are very, very close. So the y value of the tangent line is pretty close to the y value of the function. When I get all the way over here, they're not. Okay, so it really is only going to be used to approximate it when you're near the a value. Okay.